you. All right, we're going to wrap up our 5-3 notes. As a bit of refresh, 5-3 is talking about transformations of these graphs. All right, so we talked about the parabola and A, H, and K, what that does to the graph of a parabola. Right, the A value can be a stretch, compression, or a reflection depending on the value. If A is 1, nothing happens, right? It's a multiplier. 1 times anything is itself. H and K are add and subtract. So if H and K are 0, nothing happens. But if H is anything else, H is a horizontal translation, a shift left or right, emphasis on the F. K is up and down. That's your vertical. All right, so then we took a look at the parent function for square roots. All right, square root is the shape of an eyebrow. And that starting point right there is your H comma K. And we talked about how the domain is just from 0 to infinity, our range 0 to infinity. Then we took a look at the cube root function. All right, so the cube root function is no longer just an eyebrow. It is, yeah, that's a heck of a unibrow. You have one eyeball here and another eyeball here. That would be awful.
Eyeballs and earballs.
Okay, thank you. No, you're good. What we found out is the domain and range for the cube root function is all real numbers, regardless of how much you shift it or stretch it. All real numbers for the cube root function is your domain and range. All right, we graphed a couple of them. All right, this guy shifted right 5 units, so the domain changed. This guy shifted left 1 unit, otherwise everything else remained the same. Down here, we had an A value of 2, which was a stretch. Our H was -3, so we shifted to the left 3 units. Our K was 5, so we went up 5 units, so that is our H and our K is -3, 5. That started our graph. We stretched by a factor of 2, so the next closest value to the right went up 2 units. Now, where we're at now is here. Hey, I'm recording, so when people go back and listen, they're like, oh, Mr. Stevens' kids talk the whole entire time. He's a terrible teacher. I don't want them to think that. All right, so number 2. Looking at this function right here. Yes, I am very Jimmy Neutron today.
Has it been a long day?
It has indeed. What is the value of A?
Is it 1?
1/2. And what is 1/2 going to do to the parent function?
It's going to compress it.
It is a compression. Good. By a factor of 1/2. What is the value of H?
1.
Good. So what does that do to the graph?
It goes right 1.
Good job. So we're going to shift right
And then
1 unit. What is the value of K?
-3.
Yep. So we're going to shift.
Left.
No, ma'am.
Oh, down?
Yes.
Okay.
How many units?
3.
And we're going to shift down 3 units. Really, really, really good job. Now it's asking about the domain and the range.
Tell about the door, please.
So, yeah.
I need to talk to you about something.
Very well. Yep, we'll get it during Trojan time. So this is our square root function. Sorry, I'm recording, yeah. So if you think about your square root function here, the parent has a domain of 0 to infinity. And if I shift that to the right 1 unit, so take this graph and shift it to the right, 1 unit, what will the domain be?
1.
Very good. 1 to infinity. The range, right? So the range on the parent function, we read bottom to top, right? Smallest to largest y values. The smallest y value is 0. The largest goes on to infinity. But if I shift that down 3 units, what will the range be?
-3.
You got that right.
Infinity.
All the way to infinity. Good job. Okay, down at the bottom. I'm going to do this guy. Boop. So it asks us to rewrite the radical function to identify the transformations of the parent graph. So we have this function. Yeah. So this relies on the fact that the square root of two things being multiplied is the square root of the first times the square root of the second, right? That is our product property of radicals. So what can I break this into? The square root of? No, the square root
9.
of 9 times the square root of x. Now the square root of 9 you know to be 3 times the square root of x. Alright, so all of this is to say that even though I have a number inside here with the x, I can pull it out to turn that into my a value. Since a equals 3, what does that do to the parent function? What transformation does a equals 3? What is that transformation going to be?
It is going to compress by half.
Nah.
Oh, one
Gonna
number.
stretch.
Stretch by.
3.
Good.
That's so silly.
You're looking at the wrong one, aren't you?
Mm-hmm.
That's okay. That's okay. And take a look here. Right? There's the parent. And when we stretch it by a factor of 3, think about it taking the x-axis and pulling all of these up. So all the y values get multiplied by 3. All of the y values get multiplied by 3. Okay? All right. Roll it over, Smokey. Here, I'm dealing with the square root of 4x plus 16. All of that plus 7. So 4x plus 16. I don't want that 4 in front of the x. I'd like to get it out of there. But it's 4x plus 16 that's there. So what do 4 and 16 have in common?
They both can be multiplied by
They can both be divided.
4. Yeah, so if I pull a greatest common factor of 4 out, so the undoing of distribution, what's going to be left over?
X minus 4 or plus 4.
Good. So I can replace the 4x plus 16 with 4 times the x plus 4. So this function becomes the square root of 4 times x plus 4, all of that, plus 7. And since I have multiplication inside the radical, I can turn that into 2 radicals. So we have the square root of 4 times the square root of x plus 4. I don't need parentheses anymore. And plus 7. What is the square root of 4? Just 2, right? So now my h of x is equal to 2 times the square root of x plus 4 plus 7. So what is the value of a, Austin Mersman?
Don't tell me.
I'm not. I'm asking.
Let me go back and look one more time. I want to say it's 2.
You got that right. And what does that do to the graph?
It will stretch it.
Yes, good. So we are going to stretch by a factor of 2. Really, really good. Keist, what's the value of h? Let's go. Good job. And what is that going to do to the graph? Good job. Left 4 units. Jasper, what's the value of k here, big dog?
7.
You got that right. And what does that do to the graph?
Everything up 7.
Yeah, so we're going to shift up 7 units. Really good job. Really good job. Let me know when you're done writing.
I'm done.
All right, so these problems down here, we are going to skip because they're unusually difficult for no reason at all. I'm also going to skip this guy, unusually difficult for no reason at all. All right, so it wants us to write a radical function given a graph. So here's the graph, and we're going to write a function. So we need to start, whenever we have a graph and we need to write the function, the first thing we want to do is establish h and k. So, what is our h and k going to be for a? Yes, really good, but I need you to speak up, sweetie. A little bit louder, Jaden. What's our HK for this one? I know what you said, but you didn't say it properly, so I'm going to give you one more opportunity to exercise your ability to speak. Jaden, please tell me, what is the HK here? Yeah. -5, -4. That is our HK point. Right? That's where we start the square root function. So our h and k here is -5, -4. A little bit of redemption though. What would the h and k be for this cube root function? No, hk. What's that? What's the? Yeah, so 0, -2 is the hk for this function, right? That center point of the cube root function is the same as a starting point for the radical function, which would be the same as a vertex on a parabola. Okay, so we've established h and k. That means in the equation y equals a times the square root of x minus h plus k, I get y equals a times the square root x minus -5. That's silly. I'm not going to write x minus a -5. What am I going to write? Subtracting a negative is the same thing as adding. So I'm in here, I'm going to write x plus 5. My k value stays the same as -4. So step number 2, I have to use a second point to find a. So, Chloe, give me a second point on that graph. -1, -2. So -1 is the x value, -2 is the y value. So I'm going to replace this y value with -2. So -2 equals a times the square root of x, not x. I'm replacing x. Come on, Mr. Stevens, you got to be better. The x value here is -1. So we're going to say -1 plus 5, all of that minus 4. Now, to solve this equation, -1 plus 5 is 4. I'm going to add this -4 over here. I got to add to both sides. So -2 plus 4 is 2. A times the square root of 4. Now, what is the square root of 4? 2. Yeah, so 2 equals 2a. And dividing by 2, our a value here is just 1. So what radical function is represented in this graph? Y equals the square root of x plus 5 minus 4. That's the function being represented in this graph. Now we're not going to do b. For some stupid reason, it's really tough. Oh, it's a good day today. Okay, most of your homework for this section, there's only 10 problems of homework. Not too terribly difficult. Most of you can probably get it done during Trojan time today. Most of it is identifying the transformations that are happening. So, let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, that's tough.
Take the people that, like...
All right, Dally. Number 4. How many transformations do you see, Dally? Right here. The square root of x minus 2. Is there an a value that's different than 1? No. Is there an h? Yeah. Is there a k? No. So how many transformations on this one? Just one. What is that transformation, Dally? Yep.
Up 2? No, right 2. Now it's the S plus 2.
So that's an H.
Yeah.
Yeah, so we're going to shift how far and in what direction?
We're gonna shift right 2.
Yeah, good. We're going to shift right 2 units. Good. All right, Chloe, on number 5, how many transformations do you see? That's a cube root. That is not 3 times the square root. That is a index. 1 transformation. And what is that transformation? Good. We're going to shift left 2 units. Really good. Jaden Emery Peters on number 6. How many transformations do you see? 2. Good. Give me one of them.
Just 1 unit to the left.
Good. We're going to shift left 1 unit. Keist! What is the other transformation on this problem? Yeah, let's go. Good job. Really, really good. Philip, how many transformations do you see on 7? 2. Good. Give me one of them. Good. We're going to shift right 3 units. I'm all right with that. Jasper, give me the other one.
Up 2.
Good. Up 2 units. Love it. Lily on 8, how many transformations do you see? 2. Good. Give me one of them.
Oh my gosh, my nose.
Me too.
It's gonna stretch.
By a factor of? Really good. Really, really good. We are going to stretch by a factor of 3. Austin, what's the other transformation?
I'm not done yet. Down 5?
No, sir.
Then I don't know.
Is that in or out of the radical? Is it
Oh.
in the radical or out of the radical?
You should go right.
Yeah, we
5
should go right 5 units. We're going to shift right 5 units. Really, really good. Piper Gus on number 9, how many transformations do you see?
2.
Really good. Give me one of them.
Moving left 1 unit.
Yeah, is that...
Shifting
Yeah, the other's a good shift. Is that inside the radical or outside?
outside.
So is it an H or a K?
It's a K.
It's a
so
K.
It's moving up.
Good. We're going to go up 1 unit. All right. Last one, Sully.
Stretch me by 1/2.
Yeah, so if you multiply me by a half, am I getting bigger or am I getting smaller?
Smaller.
Smaller. So is it going to be a stretch or a compression? Compression. Really good job, dude. Proud of you. Compress by a half. So this is what the majority of your work is going to be on the 5-3 homework. There's only 10 problems and maybe 11, I don't know. Somewhere in that ballpark. I did not overload you on 5-3 homework.
Sure you're not lying because it's April Fool's Day, Mr. Stevens?
I promise you I'm not lying because it's April Fool's Day. I promise.